All right, old ways. You have to parameterize C. How do you parameterize this line segment? Uh, the most obvious parameterization is t, as t goes from 0 to 1. If anybody does anything, any other parameterization besides this, that could be valid, but it's really, really weird that somebody will do something besides this. Okay, this is like the most, the least sophisticated way to do this, right? Just t comma t as t goes from 0 to 1. That will take you directly from 0, 0 to 1, 1. And the derivative, of course, is just 1, 1. Now, f in this context, if x is t and y is t, this is 2tt, that's 2t square, and then x square is considered t square, right? So then you can find f dot r prime, because that's what you will end up integrating, and that would be 3t square. So the line integral, the work integral f dr, will be the integral from 0 to 1 of 3t squared dt, which is t cubed, going from 0 to 1, and that is not t, that is 1. Okay, so that's the old way. It's not too difficult, all right? But the nice thing is, I mean, sometimes this is really time consuming depending on what that vector field at capital F is. But in a new way, by the fundamental theorem of line integral, okay, you can find this much easier, I think, right? So we have to find the antiderivative or the potential function. Okay, that's what you need first. We've already done this, but let me just think about this again, right? This is supposed to be fx. This is supposed to be fy, right? So your fx has to look like x squared y plus something, right? This something is some function of y only without any x, right? The fact that this is fy, that's, okay, so the fact that fx looks like this means that the original function f has to be x squared y plus some function of y. The fact that fy has to look like this means that the original function has to be x squared y plus some function of x. Okay. Well, yeah, there is a function that looks like both of these, and that is x squared y. Now, plus a constant, of course, okay, if you want to, but you can't have any x in here because that would violate this form, and you can't have any y in here because that would violate this part, right? Remember, this part cannot have x, this part cannot have y. So the potential function will be x squared y. All right. So then by the fundamental theorem of line integrals, this line integral FDR of the curve C, which happens to be a straight line segment, is x squared y evaluated at 1, 1 minus x squared y evaluated at 0, 0. So this is 1 squared times 1, which is 1, minus 0 squared times 0, which is 0. And of course, the answer will be the same by the fundamental theorem of line integrals. Okay, so I hope you got this right, and you will hopefully have now experienced twice how much easier that fundamental, the answer is, if you happen to know what the potential function is at the beginning. All right, so this leads us, let's see, should I do another example? Yeah, let's do one more example in 2 dimensions, and then we'll go into a 3-dimensional examples. All right, so let's see, find the line integral FDR, which is a work integral, right? If your vector field is 2xy, x squared plus cosine of y, and C is any path curve from 0, 0 to 1 pi. Maybe I will draw a picture of this. Okay, so you have this 0, 0, that's the origin, and 1 pi happens to be around here, 1 comma, 3.14, whatever. Right? My C is like this. That's my C. How do you like that? Okay, so what is the, how do you do that? I mean, this C sounds, looks very random, right? But again, remember what happens is, as if this capital F happens to be a conservative vector field, and I certainly hope it is, because if this capital F is not conservative, I wouldn't know what the answer is, because that would not be path independent. And this path that I drew, C is just really weird, right? But if capital F is conservative, then we know a quick way of finding the answer to this question. All right, so let me go ahead, and this is a very standard procedure. I can go ahead and start looking for a potential function. But before that, I want to make sure that a potential function exists, okay, right? Because again, you don't want to start looking for something that you don't know if it exists, all right? So let's say QX is 2x, right? And what's py? The partial of p with respect to y is 2x. All right, so that is a conservative. So this is a quick check, and this is nice because this was quick, right? F is conservative, and therefore lowercase p, a potential function does exist, right? Now, if the potential function exists, remember fx has to be 2xy, and fy has to be x squared plus cosine of y. If fx has to be 2xy, then the original function has to be x squared y plus some expression of y only, okay, can't have x anymore. But if this is fy, then f has to be x squared y plus some, oh wait, it has to have sine of y also, right? Plus some expression of x only, which will disappear when you differentiate with respect to y. Okay, so can you think of one function that looks like both of these? Remember, you're not adding these, by the way. You're looking for one function f of xy that would look like both of these. And the answer, yes. The answer is x squared y plus sine of y plus some constant, which can be included in here as well as in here, right? So that is my potential function. And now, by the fundamental theorem of line integral, I know what this work integral is, or the flow integral along C of f dr is equal to x squared y plus sine of y evaluated at 1 pi minus this same thing evaluated at 0, 0. If you evaluate this at 1 pi, you have 1 squared times pi plus sine of pi, and sine of pi is 0, minus, and then plugging in 0 would of course just create 0 plus 0. It's not comma. And so the answer is going to be pi. Okay, so the if you're trying to find out, the work done by this strange vector field F as the sailboat goes from here and then goes around and ends up here, the answer is going to be pi, whatever the units are. All right, so that's sort of a nice application of this. What if F is three-dimensional? Okay, so that is the next question that we will address. And the answer is it's similar to if F is two-dimensional. By the way, before we go and add that extra dimension, I said that by the fundamental theorem of line integrals, the answer to the previous question was pi. If you do this in old-fashioned way, you certainly cannot go around this random curve I drew with C, right? But because this is conservative, it is path independent. So you can replace the C with any other curve from 0, 0 to 1 pi, namely, and the easiest one is, of course, the line segment from 0, 0 to 1 pi. And if you parameterize that with your standard parameterization, and you take the derivative of r, and then you find an expression of f using t, and then you can find f dot r prime, you integrate it from 0 to 1, and you will get the same answer, just as the fundamental theorem promised you would. Okay, so this is just something in this purple font I added the old-fashioned way, the non-theorem way of finding the same value for that line integral. Okay, so now let's go to the three-dimensional aspect of it. This part is going to be relatively short. Okay, but the main difference, whoops, I want to have back the same color here. The main difference is now, instead of two, I have three components for the vector field F, P, Q, and R. Okay, now we want, of course, we want this to be, I guess I should say, we want this to be Fx, Fy, Fz, right? If the potential function has the gradient of F is to be capital F, right? So that is the requirement for conservative, right? Conservative, if F is to be conservative and path independent, then F, which is PQR, must be Fx, Fy, Fz. Now, what do we know about these mixed, the second derivatives? Well, we know F of xz is equal to F, maybe I should start with the correct, let's do this in alphabetical order. Xy and Yx must be equal to each other. F of xz must be equal to F of zx, right? And finally, F of yz must be equal to F of zy. So let's, and this is an easy process here. Okay, we know Fx is P, Fy is Q, and Fz is R, right? So let's put these in a new language here. F of xy is Py, okay? And F sub yx is the middle one. Remember, F of yx will be the middle one with respect to x, so that would be Qx. This is the same as before, okay? We in the two-dimensional case, Qx had to be equal to Py because F of xy and F of yx must be equal to each other. This time I have Fxz, that would be this with respect to z, that's Pz must be equal to Fzx, that would be Rx. And then F sub yz, so that would be this with respect to z, that's Qz, must be equal to F sub zy, so that's Ry. That's really complicated, right? Or it appears to be complicated, but that's all of these three statements must be true if the three-dimensional capital F, a vector field, is to be conservative. This is a little complicated, but there's a nice, easy way to remember this, right? And here's the picture, and you probably should remember this picture. Maybe I should do this in different color here. What you have is three components, P, Q, and R, okay? And you have X, Y, and Z. And what the three statements are telling you is this, okay? If you draw the cross out, let's do the first and second. You cross the first and second, okay? So Py must be equal to Qx. If you pick the first and third, it says, and that's the second one, okay, the second one here, Pz must be equal to Rx. Right? And then the third one says Qz must be equal to Ry, that's Qz and Ry. So if you remember this picture, okay, I think that would be a lot easier to remember these three components or conditions, okay? I'm gonna do this again. You ready? This is a dynamic way of teaching because I am continuing to erase and then do this writing again. All right, let's make sure that we understand these three components or the three facts to be checked, three equations to be checked for capital F to be conservative and the lowercase f is a potential function. Py must be equal to Qx. Pz must be equal to Rx. And Qz must be equal to Ry. All right, so that's what you need to do. All right, let's practice. I don't have too many examples here, but is this a conservative vector field? All right, I'm going to give you a challenging one. Ex cosine y plus yz. X z minus e to the x sine of y. I worked hard to find this example. No, not really. Okay, so is this vector field conservative? That is the question. Now, you could go ahead and try to find a potential function. Okay, so potential function would be, f so that the gradient of lowercase f is f. That means you want this to be fx, this to be fy, this to be fz. Okay, but I strongly recommend that you find out that this is conservative first. Okay, in other words, if you start looking directly for lowercase f, there's still a chance that this capital F is not even conservative, and therefore the lowercase f does not exist. And once again, I should tell you, you really shouldn't spend time looking for lowercase f if that lowercase f does not exist, because you will not find one. Okay, so that's why I'm saying you should check it, check to see if it's conservative by this three-part check. Okay, so this is called P, this is called Q, this is called R, right? And so the first thing I have to do, and I usually, even write something like this, right? So let's check this first. Is Py equal to Qx? Okay, that's my first check. Let's take the derivative of P with respect to y. What do you get? Well, that's negative e to the x sine of y plus z. You see that? This is P. So I take the partial of this with respect to y, and I get e to the x, negative e to the x sine of y plus z. Qx, what's Qx? That would be z minus e to the x sine of y. Do they look the same? No, they don't look the same, because this first one starts with negative and then second one starts with z. Oh, wait a minute, but that's not the case, right? This actually is equal. These are equal to each other. It's just that the order is reversed. So that's okay. The first test passed. Second test, is pz equal to qx? Pz, so take this, differentiate it with respect to z. Well, that's an easy one. That's just y, okay? And then qx, let's say, no, this is not qx. This is supposed to be rx, right? Rx, see, a typo or misspelling could cost you a lot of time, so be careful. Because in the second part here, I am checking pz and rx, right? So what's our rx? Take this, differentiate it with respect to x, you get y. Great, the second one passed. The last one is qz and ry. So qz, let's differentiate this with respect to z, and you get x. Differentiate r with respect to y, and you get x. All right, so that looks like good news, bad news, right? The good news is it is conservative. Bad news, because it's conservative, now you actually have to find the lowercase f. Okay, because if it's not conservative, you don't even have to find this lowercase f. But now let's find that. Let's find this lowercase f antiderivative potential function. Remember, fx has to look like this. It looks like p. Okay, fx must be p, which is ex cosine y plus yz. This is after you take the derivative with respect to x. And this means the potential function must look like e to the x cosine of y plus xyz plus, and you could have any function of y and z as long as x does not appear. I hope this is clear, because I've done this a few times now, right? It's okay to have some expression of x and y and z, but you can't have any more x in here, because if you have any x in here, when you differentiate it, you will have an extra term, right? All right, so fy has to be this q, and the middle one is xz minus e to the x sine of y, and xy plus z. Let me just go ahead and write this. The last one to check is this, right? All right, so the middle one says my f must look like q if after being differentiated with respect to y. So you have to have x, y, z in order to have this term. And then in order to have negative e to the x sine y, I have to have plus e to the x cosine of y, because that's the only way you can get negative e to the x sine of y. Now, you could also have something, as long as that something consists of constants x and z, but no y. Okay, so my potential function has to look like this, and it also has to look like this. And one more thing, because after you differentiate f with respect to z, you get this r, which is xy plus z. I must have xyz. And in order to have this, what would I have to have in the original function? Yeah, 1/2 z squared. That would happen to be the antiderivative of z, right? You have to have this, and then you can have any expression of x, y, and constants. My one function, f, remember now I am not adding these. Some students tend to add these for some reason, but you don't add these. My function y, one function y has to look like all of these. All right, therefore, f, any potential function is a function of x, y, z such that it will look like this. E to the x cosine of y has to be there. That's this, okay? And it must be included in here because it doesn't appear in the rest of the third, this part here, okay? It also has to have x, y, z because this appears here and here and here, right? Okay, and then is there anything else here? Well, see, for this, that would satisfy this part here. It would also satisfy this, but it would not satisfy that because I still don't have 1/2 z squared, which has to be there because my f sub z has plus z in it, right? Now, this equation plus a constant would satisfy my first condition, my second condition, and my third condition. Now, the third condition doesn't have cosine of y in it, but that's okay. It must be that this whole thing is included in G3xy, right? Remember, I could have any expression of x and y here as long as there's no z. So this, therefore, this is my potential function. This is my correct potential function. And by the way, this is the most general potential function. You don't even have to have plus c. If I ask you to find a potential function, you can just skip that plus z in it, okay? If you ask for the most general form of the potential function, then you would have to have that plus c in it, okay? Let me ask you a follow-up question, all right? Evaluate this. The integral of this, the work integral of f, which is f dot dr, you can also write this as p dx plus q dy plus r dz, if you like. Okay, it is a work integral in three-dimensional space. It's also f dot t of ds, right? Because that's the same thing. So maybe I should write both of these. I think the most common expression for this work or line integral is actually f dr, because like I said last time, FDR is forever associated in American history with work. And so it makes sense to have work integral as FDR. Find FDR if C is any curve from the origin to 0, 0, 2. Okay, so it could be a straight line from 0, 0, 0 straight up to 0, 0, 2, or it could be just winding and winding around from 0, 0, 0 and eventually end up in 0, 0, 2. It doesn't matter what kind of curve it is, as long as this is the starting point, initial point, and this is the terminal point. The answer, by the fundamental theorem of line integral, this happens to be e to the x cosine of y plus xyz plus 1/2 z squared evaluated at 0, 0, 2 minus this expression evaluated at the origin. Okay, let's try to evaluate this at 0, 0, 2. This will be, well, oh, that's not 0, is it? Because this will be e to the 0th. Maybe I should write this down. E to the 0th cosine of 0 plus 0 times 0 times 2 plus 1/2 2 squared. That is the first part. Second part is e to the 0th cosine of 0 plus 0, 0, 0 plus 1/2 0 squared. Okay, of course, that last part is, well, okay, let's figure this out. This part is actually not even 0 here, right? It's 1. But of course, it's going to cancel with this, so I guess it doesn't matter. But it's 1 plus 0 plus 2 minus 1 plus 0 plus 0. Okay, so it turns out to be 2. That is the answer to this question. How much work is done by vector field F along the curve from 0, 0, 0 to 0, 0, 2? And the answer is 2. All right, now I have used the fundamental theorem of line integral a few times here, right? Here's a corollary. I hope you know what a corollary is, or as a British person would say, a corollary. Okay, a corollary or corollary is a statement that directly comes from another statement, which is basically a theorem. Right. So this is like a byproduct of a theorem. It is a sort of an overflow of a theorem. It is a direct consequence of that theorem of which we call the fundamental theorem of line integrals. Right. What I said is it doesn't matter if you go from A to B in this way or in any other way, right? So guess what? If this here, C1, C2, okay. If F is conservative, what I said is the integral of F dr C1 is equal to F dr of C2, okay? Therefore, if you remember, C1 union C2 is a loop. Now, I have to explain what a loop is in just a second, okay? But C1 plus C2 will be just this, okay? It goes from A to B and then comes back from B to A because, oh, sorry, it's C1 union minus C2 is a loop, okay? And because this, and of course the negative of this, it would be exactly the opposite. And therefore, the C minus C union negative C2, the loop, okay, F of dr is going to be 0. Why? Because you go, let's say if this is 5, then this will also be 5, right? So it's 5 plus negative 5, and it's going to be 0. Okay, so here's the corollary. What I wrote here is really not the corollary itself. The corollary is if F is conservative, and if C is closed, okay, and that means C goes from a point to the same point. Okay, in other words, if it starts and ends at the same, if it starts and ends at the same point, like this picture here, it goes from A back to A. If C is a closed curve, which we call a loop, okay, if it's a loop, then the integral, the line integral of F dr is always going to be equal to 0. Okay, it's as if nothing happened. You went and came back and nothing happened. And by the way, this is why that lowercase f is called conservative, or capital F is called conservative, because the energy is conserved as you go around. It's as if nothing happened, right? If the total replacement is total replacement is 0. So that is an important segment here. If F is conservative, and by the way, this is obvious. Because in this case, you know what this is? It's going to be the potential function evaluated at A minus potential function evaluated at A, right? Because the start and end points are the same. So that's why this corollary is true, okay? So with that, I think we are pretty much done. I think you can do all the homework exercises from section 3 at this point. All right, so section 3 has been a relatively long section, but it's really not all that complicated. I think you can easily find a potential function if capital F happens to be a conservative vector field. All right, and so you are given I don't know, probably a dozen exercises. I don't think any of them are really difficult. Some of the calculations could get a little messy because the functions could be quite messy, but but nothing really difficult. All right. So I hope you will go and do your homework and get this thing down. I think I'm sure you can master this section. And then we'll go into named theorems from now. I know we had one theorem, which is the fundamental theorem of line integrals. By the way, anytime a statement or a theorem in mathematics has an extra name, as opposed to just like, theorem 1.2 or theorem 2.5.2 or something, if a theorem has a name, it's probably because it's important, okay? So the fundamental theorem of calculus is of course important. The fundamental theorem of line integrals is also important. Now in the next section, we'll talk about another one of those named theorems called Green's theorem, okay? And it will be followed later in a chapter by Stokes' theorem and the divergence theorem, okay? So those are some of the major highlights coming up in this chapter. All right, I hope you'll have a great week. Take care. See you. Bye.